Alpha Carbon Chemistry, Enols and Enolates, Chapter 21. Objectives: 1. The alpha carbon. 2. Alpha carbon halogenation. 3. Aldyl addition reactions. 4. Claisen condensation. 5. Alkylation of the alpha carbon. And 6. Synthetic strategies. Your goals. By the end of the chapter, you should be able to identify the alpha carbon of a carbonyl, the enol, and the enolate ion, write mechanisms for reactions covered, understand and predict the reactions under acidic conditions and basic conditions, write reactions involving halogenation, aldyl addition, Claisen condensation, and alkylation. Predict synthetic steps. 1. The alpha carbon. Greek letters are used to describe the proximity of carbon atoms relative to the carbonyl group. This chapter will primarily explore reactions that take place at the alpha carbon, and alpha protons are the protons attached to an alpha carbon. Alpha carbons are carbons that are directly attached to a carbonyl carbon. Most reactions covered here will proceed via an enol or enolate intermediate. What will depend on is whether or not the conditions are catalytic acid or base, or there's a strong base present. The enol or the enolate ion are intermediates that will then result in a reaction taking place on the alpha carbon. Oftentimes there's going to be an addition of X. Enols. In the presence of catalytic acid or base, a ketone or an aldehyde exists in equilibrium with an enol. An enol is a compound that has on an sp2 hybridized carbon a double bond and an OH group. The ketone and the enol are tautomers of one another. Equilibrium generally favors the ketone. But there are exceptions where the enol form is favored at equilibrium. The enol of a 1,3-diketone is stabilized by conjugation and intramolecular H bonding. It is more stable than a typical enol and will be favored at equilibrium. Phenol is another example where the enol is vastly favored over keto at equilibrium. Phenol is an enol with aromatic stability. Acid versus base catalyzed tautomerization. The mechanism for tautomerization depends on whether it is acid catalyzed or base catalyzed. Let's consider the mechanism for acidic conditions. Under acidic conditions, the carbonyl group is first protonated to form a resonance stabilized cation. The second step is a proton transfer. The cationic intermediate is deprotonated to give the enol form. Under basic conditions, in the first step, the alpha position is deprotonated by the base to form a resonance stabilized anion. This anionic intermediate at the end may be protonated to give the enol. The alpha position as a nucleophile. In acidic conditions, it is safe to assume that some fraction of a ketone or aldehyde in solution will exist in the enol form. The alpha position therefore will be nucleophilic because it is electron-rich. We can see the electron richness by looking at the resonance structures. In basic conditions, because in the presence of a strong base, the enolate forms, the enolate is much more nucleophilic than the enol and will carry an overall negative charge. It is also resonance stabilized. C versus O attack. The enolate can undergo carbon attack or oxygen attack. If the alpha carbon attacks, it is the nucleophile and attacks an electrophile, forming a new sigma bond between the alpha carbon and the electrophile. If the oxygen attacks, it is the nucleophile, and it will make a new sigma bond between the oxygen and the electrophile. Enolates generally undergo carbon attack. which is drawn in one of two ways depending on which resonance form of the enolate is used. Most of the reactions in this chapter will involve enolates. Acidic protons and base selection. The alpha carbons protons are the only acidic protons on an aldehyde or ketone that can be removed to form an enolate. The beta or gamma protons are not acidic enough. Deprotonation will not yield a resonance-stabilized intermediate. The pKa value of alpha protons must be considered when choosing an appropriate base to form an enolate. In the table, we see some pKa values of common ketones and aldehydes: acetone, acetophenone, and acetaldehyde, having pKa values of 19.2, 18.3, and 16.7 respectively. Reversible reactions. When pKa values of a base and the enolate are similar, both products and reactants are going to be present in significant amounts. When the alkoxide is used, the enolate, which is the nucleophile, can react with the ketone, which is an electrophile, but this will be in equilibrium because the pKa's are extremely close. Irreversible reactions. To irreversibly and completely form an enolate, a stronger base must be used, like sodium hydride. Hydride is a strong enough base to abstract the alpha proton, and that will release hydrogen gas as well as the enolate. Another strong base is LDA that is commonly used to form enolates irreversibly. LDA is made by treating diisopropylamine with N-butyllithium. LDA stands for lithium diisopropyl amide. When LDA is used to form an enolate, the amount of ketone present at equilibrium is negligible due to the very extreme differences in pKa values that will then favor the right, which is the product side, due to being a weaker acid at pK 36 compared to the pK 16.7. LDA features two bulky isopropyl groups, which allows it to be a strong base, but not a good nucleophile. Increased acidity. When protons are alpha to two carbonyl groups, they are much more acidic. Note here, with only one carbonyl group, the pKa of the alpha proton is 16.7. With two carbonyl groups, the pKa of the alpha protons is 9. The increased acidity is due to increased stability of the resulting enolate. It has more resonance structures, resulting in increased stability. Deprotonation. 1,3-dicarbonyls are acidic enough to be irreversibly deprotonated by an alkoxide. There will be no need in this case to use sodium hydride or LDA to form the enolate. Of a 1,3-dicarbonyl, it would be considered overkill. In other words, an alkoxide is basic enough in this case to push equilibrium to the right. Synthetic strategies. It is important to know what base to use to generate an enolate, depending on the carbonyl compound and the desired result, reversible versus irreversible. We studied earlier that if we have an alpha carbon with alpha hydrogens, sodium hydroxide or sodium ethoxide, or a different type of an alkoxide, will result in both the enolate and the ketone form being present at equilibrium. One would use a stronger base like sodium hydride or LDA to obtain the irreversible enolate formation. If, though, the alpha hydrogens are much more acidic due to 1,3-dicarbonyls, sodium hydroxide or sodium ethoxide, or a different kind of alkoxide, it would be strong enough in order to form the nearly complete enolate. LDA is not necessary. 2. Alpha carbon halogenation. Under acidic conditions, ketones or aldehydes undergo alpha halogenation. This will work well with chlorine, bromine, and iodine, but not fluorine. Acidic conditions means an enol is the reactive intermediate. Mechanism. Halogenation under acidic conditions mechanism has two parts. Part 1 is the enol formation. The proton transfer occurs first, where the carbonyl group is protonated to form a resonance stabilized cation. Another proton transfer results in the cationic intermediate being deprotonated to give the enol form. The second part is the halogenation step. Nucleophilic attack occurs first. The enol functions as a nucleophile and attacks the molecular bromine. Proton transfer occurs next. A proton is removed to afford the product. Unsymmetrical ketones. When an unsymmetrical ketone is used, halogenation occurs faster at the alpha carbon that is more substituted. If we consider the more substituted alpha carbon, it will create the more stable alkene compared to the less substituted alpha carbon having a less substituted alkene. The major product then results from the more stable or the more substituted enol form. In this example here, the major product will be the halogenated product at the tertiary carbon instead of the secondary carbon. This will be the minor product. Two-step synthesis to an alpha-beta unsaturated ketone. Alpha halogenation provides a two-step synthesis for the synthesis of an alpha-beta unsaturated ketone. Other bases can be used for the elimination, which includes tert-butoxide or lithium carbonate. In the first step, we would have the formation of the halogenated ketone. Elimination would then result in the alpha-beta unsaturated ketone. On alpha carbon, we have the carbonyl. On beta carbon, we have the alkene. The Hell-Volhard-Zelensky reaction, or the HVZ reaction. In this reaction, there is bromination of the alpha carbon of a carboxylic acid. A carboxylic acid first reacts with bromine and phosphorus tribromide, and then followed up and work up in water. The mechanism is believed to be the following sequence. In the first step, PBr3 and the carboxylic acid react to form an acid halide, which is in equilibrium with an acid halide enol. This is then followed by bromination with Br2, and then the workup with water results, with the alpha carbon having been brominated. Alpha halogenation, basic conditions. Alpha halogenation can also be basic conditions. Alpha halogenation can also be achieved under basic conditions. Under basic conditions, an enolate is the reactive intermediate. Let's consider the mechanism. In the first step, the base, in this case hydroxide, abstracts the alpha proton. As it abstracts alpha proton, the sigma bond becomes a lone pair on alpha carbon. The enolate ion is formed. It then reacts with bromine, in this case, by abstracting one of the two Brs, and the sigma bond between the two Brs breaks and becomes a lone pair on the Br, resulting in bromide. Now we have the alpha halogenation of this ketone. Under basic conditions, polyhalogenation typically results. It cannot just be stopped oftentimes with one. Once a ketone is brominated, it will form an even faster enolate intermediate and brominates again at an even faster rate. Haloform reaction. Under basic conditions, methyl ketones are converted to carboxylic acids using excess halogen and hydroxide. After the three alpha protons are replaced, the CBr3 group acts like a good leaving group and acyl substitution occurs. In the mechanism, the first step is nucleophilic attack. The base, hydroxide, attacks a carbonyl carbon. At the same time, the pi bond breaks and becomes a lone pair on the oxygen. The lone pair comes back down. At the same time, the good leaving group leaves, CBr3 minus in this case. The resulting carboxylic acid is deprotonated under the basic conditions. This forces the reaction to completion. CBr3 minus pulls off H+, resulting in the carboxylate ion, and in this case, bromoform. One may use Br2, Cl2, or I2. This is a synthetically useful way to produce carboxylic acids from methyl ketones. And this will work best if the other alpha carbon has no alpha protons. 3. Aldyl addition reactions. Recall that when an aldehyde is treated with hydroxide or an alkoxide ion, an equilibrium forms where significant amounts of both enolate and aldehyde are present. If the enolate attacks another aldehyde, an aldyl addition reaction occurs. The product features both aldehyde and alcohol groups. Note the location of the hydroxide group on the beta carbon. Aldyl addition basic conditions. Under basic conditions, an enolate is the reactive intermediate. Aldyl addition mechanism. In the first step, there is a proton transfer. The alpha position is deprotonated to form an enolate. The second step is nucleophilic attack. The enolate ion serves as a nucleophile and attacks the aldehyde's carbon. Then proton transfer. The resulting alkoxide ion is protonated to give the product. The aldyl addition is an equilibrium process. For most simple aldehydes, aldyl product is favored. Most of the product will be the aldyl product, as shown here in this example. For most ketones, the aldyl product is not favored, and we'll see then the ketone is the favored. Retroaldyl reactions. The reverse process is called a retroaldyl reaction. The mechanism is simply the reverse of the aldyl addition. In the first step, there is proton transfer. The beta hydroxy group is deprotonated by a base. The second step is the loss of a leaving group. The carbonyl group is reformed, expelling an enolate as the leaving group. Then proton transfer. The enolate is protonated, regenerating back, in this case, the ketone. Aldyl condensation. When an aldyl product is heated under acidic or basic conditions, an alpha-beta unsaturated carbonyl forms. This is called an aldyl condensation. Condensation. This refers to reactions where two molecules undergo addition and a small molecule, like water, is lost. Aldyl condensations occur when the aldyl addition is performed at elevated temperatures. Oftentimes we will denote this with the word heat. Effective temperature. Aldyl condensation occurs when an aldyl addition is performed at elevated temperatures. We will see aldyl addition and then aldyl condensation if the temperature is increased. Aldyl condensation mechanism. This is a two-part mechanism, with part 1 being the aldyl addition. In the first step, there is proton transfer. The alpha position is deprotonated by a base like hydroxide to form an enolate. In the second step, it's nucleophilic attack. The enolate serves as a nucleophile and attacks an aldehyde. This is followed up by proton transfer. The resulting alkoxide ion is protonated. Part 2 is the condensation step, elimination in this case of water. The first step is proton transfer. The alpha position is deprotonated to form an enolate. The second step is loss of a leaving group. Hydroxide is ejected to afford the product. Steric considerations. Steric considerations. When two stereoisomeric pi bonds can be formed, the product with fewer steric interactions is the major product. So in this case, we will see as our major product the trans alkene instead of the cis alkene. Favored product. Because the aldyl condensation is favored, often it is impossible to isolate the aldyl addition product. And the yields for condensation are typically much greater than yields for the addition product. If we have, for example, this reaction in the presence of a base but at 10 degrees Celsius, the yield for the addition product will be about 20%. At elevated temperatures, the condensation product yield is about 90%. Cross-aldol reactions. Two different aldehydes or ketones react in a cross-aldol reaction, or a mixed aldol reaction, and may yield 4 possible aldol products. So imagine having 2 different aldehydes in the presence of hydroxide. These are the different options that these two reagents may react in, resulting in 4 different products. Practical cross-aldol additions. Cross-aldol reactions are only practical if the number of products can be minimized, which is achieved in only one of 2 ways. 1. One of the substrates is relatively unhindered and without alpha protons. This is possible when only one compound can form an enolate and the other compound reacts with the enolate faster. For example, formaldehyde has no alpha protons, and therefore it can react with this aldehyde here to form one product. 2. The use of LDA as a base, or i.e. a directed aldol addition. One compound is completely converted to enolate with LDA, the other carbonyl compound is then slowly added to the enolate. So here we have the formation of the enolate by working with something like LDA to form it, and then we add the second aldehyde to the solution containing the enolate slowly to generate the product. Intramolecular aldol reactions. Intramolecular aldol reactions form cyclic compounds. One group forms an enolate that attacks the other group. Only 5- and 6-member rings form well this way. Note that here we have the formation of the enolate. This is going to be the nucleophilic site, and this will then attack the electrophilic site. 4. Claisen condensation. Esters may undergo reversible condensation reactions, forming a Claisen condensation product or a beta-keto ester. This type of reaction is called a Claisen condensation. Claisen condensation is simply a nucleophilic acyl substitution reaction. The nucleophile will be the enolate of an ester and the electrophile will be an ester. Claisen condensation mechanism. In the first step, there is proton transfer. The alpha position is deprotonated to form an ester enolate. This is followed by nucleophilic attack. The enolate serves as a nucleophile and attacks an ester, forming a tetrahedral intermediate. The next step is loss of a leaving group. The carbonyl group is reformed by ejecting an alkoxide ion. And lastly, the proton transfer. The alpha position is deprotonated to form a doubly stabilized enolate. After this step, the last step, the deprotonation of this beta-keto ester, this is what drives the reaction to completion. Acidic workup is necessary to obtain the neutral product. Claisen condensation limitations. There are some limitations to the Claisen condensation. 1. The starting ester must have 2 alpha protons, because removal of the second proton by the alkoxide ion is what drives the equilibrium forward. And 2. Hydroxide cannot be used as a base to promote Claisen condensations. Otherwise, ester hydrolysis occurs. Note that we would have the hydrolysis product instead of the condensation product. 3. An alkoxide that matches the OR group of an ester is needed, otherwise transesterification occurs. If we have a different OR minus group, we end up with transesterification as our product. Cross-Claisen condensations. These are only useful if one of the following criteria is met. 1. One of the esters has no alpha protons, such as this example here, or It is performed as a directed Claisen condensation with LDA as the base. Just like before, LDA is used to form the enolate ion, and then the ester that is going to be reacted upon is added slowly to the reaction mixture. Intramolecular Claisen. These condensations can be achieved and are called Deichmann cyclization reactions. Like aldol reactions, these cyclization reactions prefer the formation of 5- and 6-membered rings. 5. Alkylation of the alpha carbon. The alpha position can be alkylated when an enolate is treated with an alkyl halide. In the first step, in this example, a ketone is reacted with a strong base, LDA, followed by reaction with an alkyl halide. The enolate attacks alkyl halide via an SN2 reaction. As an SN2 reaction, the enolate is the nucleophile and attacks the electrophile, the alpha carbon of the alkyl halide. Considerations for alpha carbon alkylation. 1. Typical SN2 restrictions apply when secondary or tertiary alkyl halides are used. E2 elimination dominates. 2. The aldol reaction also competes with the desired alkylation, so a strong base such as LDA must be used. 3. Regional selectivity is an issue with unsymmetrical ketones, as two different enolates can form. In the example given above, the enolate that may form might be the thermodynamically stable enolate, which is the more substituted enolate, or the kinetically formed enolate, which is the less substituted enolate. The thermodynamic is more stable, the kinetic is less stable but forms faster. Considering the potential energy diagram, we can see that the kinetic product forms a lot faster, but is the less stable. Thermodynamically, that is the more stable. Kinetics and thermodynamics. The kinetic enolate is favored by irreversible conditions. The way to achieve this is by the use of LDA, for example, at a low temperature, followed by halogenation. Then we achieve the product that is the kinetically favored product. Or the thermodynamic enolate is favored by the use of reversible conditions. For example, using sodium hydride at room temperature, followed by the alkylation, results in the thermodynamically favored product. Malonic ester synthesis. In the malonic ester synthesis, an alkyl halide is converted into a carboxylic acid with 2 additional carbons. Diethylmalonate is the starting material. It is first reacted with a base to form the corresponding stabilized enolate. The enolate is then reacted with an alkyl halide via SN2. Both ester groups are then hydrolyzed. One of the resulting carboxylic acid groups is then decarboxylated with heat. 1,3-dicarboxylic acids undergo decarboxylation in a pericyclic process that results then in the product and carbon dioxide. Malonic ester synthesis example and dialkylation. In this example, malonic ester is first treated with a base to form the enolate ion. It will then behave as a nucleophile and attack an alkyl halide. The workup includes acidification and heating in order to produce the carboxylic acid. Diethylmalonate can also be dialkylated. If the first 2 steps are repeated, first deprotonation followed by SN2, reaction with an alkyl halide, then the dialkylated product can be worked up in the presence of acid and heat to form the product. Acetoacetic ester synthesis. This is analogous to the malonate synthesis. It converts an alkyl halide to a methyl ketone with 3 new carbon atoms. Conjugate addition reactions. Recall the alpha-beta unsaturated carbonyls are made via the aldol condensation. Alpha-beta unsaturated carbonyls have 3 resonance contributors. Due to those 3 contributors, the beta carbon and the carbonyl carbon are electrophilic positions or electrophilic sites. Either carbon can be attacked depending on the nucleophile used. Grignard and Gilman reagents. The Grignard reagents typically attack the carbonyl position. This is called 1,2 addition. But Gilman reagents will generally attack the beta position. This is called 1,4 addition or conjugate addition. In the general mechanism for conjugate addition, the nucleophile attacks the beta position, forming the enolate. The enolate is neutralized to form the enol. The enol then tautomerizes to the aldehyde or to the ketone. Nucleophile strength and Michael reaction. Stronger nucleophiles will tend to go towards a 1,2 addition. Less reactive nucleophiles tend to do conjugate addition or 1,4 addition. Typical enolates often give a mixture of 1,2 and 1,4 addition products. Stabilized enolates will give 1,4 addition products exclusively. This conjugated 1,4 addition is called a Michael reaction. For example, if that's all that is exclusively obtained using this example reaction here, it is a Michael reaction. A Michael donor is a nucleophile that does the conjugate addition. The Michael acceptor is the alpha-beta unsaturated carbonyl. Michael donors. Here is a list of common Michael donors and Michael acceptors. Any one of the Michael donors will react with any one of the Michael acceptors to give exclusively the 1,4 conjugate addition product. Stork-enamine synthesis. Because singly stabilized enolates do not give high-yielding Michael additions, Gilbert Stork developed a synthesis using an enamine intermediate. Recall how an enamine is made, taking a ketone and reacting it with a secondary amine. Enamines. Enamines behave like enolates. They are nucleophiles. But an enamine is less nucleophilic and is a Michael donor. After conjugate addition, aqueous acid converts both groups into carbonyl groups. This is a 3-part process. The overall 3-part process is called a Stork-enamine synthesis. This is a 3-part process. The overall 3-part process is called a Stork-enamine synthesis. In the first step, the formation of the enamine. Step 2, Michael addition, followed by hydrolysis. Robinson annulation. This is a 2-step process for forming a ring. Specifically, 1, Michael addition occurs first, and then this is followed by 2, an intramolecular aldol condensation. 6. Synthetic strategies. Some reactions in this chapter result in halogenation at the alpha carbon. But most of the reactions in this chapter are C-C bond forming and yield products that contain 2 functional groups. Aldol reaction and/or condensation, Claisen condensation, Stork-enamine synthesis, i.e. a Michael reaction. The positions of the functional groups in a target compound dictate what reactions can be used to synthesize it. Let's review. Alpha halogenation. Halogenation may occur with ketones, carboxylic acids via the HVZ reaction, methyl ketones in a haloform reaction. Let's review aldol reactions. The key reactions: aldol addition under lower temperatures and condensation under higher temperatures, cross-aldol condensation, intramolecular aldol condensations. Let's review the Claisen condensation. The key reactions: Claisen condensation, intramolecular Claisen condensation known as Deichmann cyclization, cross-Claisen condensations. Review of alkylations. The key reactions: via the enolate ions, malonic ester synthesis, the acetoacetic ester synthesis, the alpha position of an enolate attacks an alkyl halide, a Michael donor attacks the beta position of a Michael acceptor. Review Michael additions. The key reactions: stabilized carbon nucleophiles, the Stork-enamine synthesis for 1,5-dicarbonyl compounds, the Robinson annulation, the formation of rings.